Good afternoon, everyone. It's really a pleasure today for me to introduce Professor David Srolovitz. This is our 38th NCCR MARVEL Distinguished Lecture. Professor Srolovitz holds the chair of materials theory and is the Dean of Engineering at the University of Hong Kong. He received his BA in physics from Rutgers and his master's and PhD degrees in material science from the University of Pennsylvania. He's the author of over 500 research papers on many different topics, including materials theory and simulation of defects, microstructure, deformation, and film growth. He served as a professor and in several leadership positions at universities across the world, including Princeton, University of Pennsylvania, the University of Michigan, Yeshiva University, and the City University of Hong Kong. He's also won numerous awards. I'm not going to list all of them, but they include things like the MRS Materials Theory Award, and he's also a member of the U.S. National Academy of Engineering, fellow of the MRS, TMS, ASM, and the Institute of Physics. So please join me in welcoming Professor David Srolovitz.
So it's a pleasure. Do I need the microphone? So it's a pleasure to be back at EPFL. It's been several years since I've been back, and when I was looking to see who I should be speaking to, I was here. There's all these people here who I know their names very well, but never really spent time with them. So it's a pleasure to be here. And some of us go back quite a long way. Roland and I actually had a research project together 20 years ago. I don't even remember how many years ago, a long time ago. Okay, so let me tell you first what I'm going to talk about and what I'm not going to talk about. So maybe I'll start with what I'm not going to talk about. So I'm not really going to talk about simulation methods per se. You know, I'll use a lot of fairly standard techniques and combine them to try to make a point about a physical problem. And the physical problem I'm going to be talking about is the result of an accidental discovery that we made recently. And I would say if I go back over my career, in fact, I've made this discovery many times, but I always thought it was just noise. It was just like bad statistics, and I couldn't afford to do more. So the project, the topic today is really just a question that goes back to some fundamental ideas in material science. And I hope to show you that when we talk about how defects move, there's some very fundamental things that we sort of missed. And there's interesting macroscopic consequences. So I'll get into that in a minute. So first, let me start by introducing the people who did the work. Tsai Hao's a great graduate student, a research group who did most of the simulation work. Xixi Wang, Mike works with Professor Marco Savonaglio at TU Dresden on phase field atom methods. And I'll show you at the end some of the experimental verification of the work that I'll be talking about done by Yan Tian and Ying Han, who are in the group of Xiaoxing Can at the University of California, Irvine. Like I said, in the simulations, there are many things that we saw previously that we kind of ignored. And if you go back in the experimental literature, you'll also see there are many good experimental examples, but we never really appreciate what they were. So let's start at the beginning. So I'm going to be talking specifically about how grain boundaries move. Now, a lot of what I'll tell you, folks, is specifically in grain boundaries, but also applies to other interfaces in materials, as well as other defects, such as dislocations, because the arguments I'm going to make are basically symmetry arguments, as I'll show you. Okay, so how do we start? So first, Normally, when we're talking about how defects move in crystals, we're thinking about the motions being overdamped. That is to say, there's no momentum, the velocity is proportional to whatever the driving force is. And this thing we call mobility is just a coefficient that actually connects those two things. Fundamental assumption, we use it all the time. In grain boundaries, in fact, it's a little bit more complicated because if I have a grain boundary here, I can talk about its motion this way. It's normally what we mean by grain boundary migration. But it's also true that if I put a shear on the material, the two crystals can shear this way. And when I put on the shear like that, how fast the two crystals move that way is basically a tangential component of velocity. So in that sense, the mobility is a second rank tensor. It's a 3x3 corresponding to motion this way, this shear motion this way, or the shear motion like that. I'll show you examples. Now, one of the necessary conclusions of all this is if I switch the sign of the driving force, the boundary moves with the same velocity in the opposite direction. Well, it turns out that this is rarely true. Even though we always assume it, we use it in all sorts of macroscopic simulations. And in fact, it's rarely true for most types of defects, whether we're talking about dislocations or two-phase interfaces or grain boundaries. So the mobilities are basically not the same when you move the grain boundary this way and that way. Now, that's a bit surprising. And I think it's surprising in part because originally when I started thinking about this, it seemed to violate some very basic statistical mechanics ideas. I originally thought that this can't possibly be true because it violates a thing called detailed balance. Turns out that that's not an issue, but it's one of those fundamental questions we have to think a little bit more carefully about. And if I go back and look at this observation, the boundaries can move at different velocities in different directions when you switch the sign of the driving force. If you go back in the experimental literature, there's many examples, some done by McCarthy and Rupert, where they show one example of this, the experiments by Dmitry Molodov in Aachen. So there are many examples. And as I was saying before, this is also one of those things where we've seen this before too, but I always thought just we didn't have good enough data. Okay, so just a reminder. Those, I spend a lot of time thinking about grain boundaries and other kinds of interfaces. So just as a reminder, a few pictures of some interfaces. So when we talk about grain boundaries, we're just talking about the two-dimensional interface that separates the same crystal structure with different orientations. So it's the plane across which the orientation changes. And for this simple case here in copper, you can see that this grain boundary has a nominal grain boundary plane like that, but you see it's a little bit more complicated. You see facets, right? The actual boundary plane seems to go like that. It's actually very common, and this is on the nanometer scale. You also, some crystals have this on the macro scale. So if you take something simple like salt, sodium chloride, of course these crystals are faceted, but this is faceted not on a macro scale, but on a nano scale. So we call this nanofaceting. In some materials, and this is just an example from rhenium, this is a hexagonal close-packed material, and this is a very perfect twin. That it's a mirror plane across here. So that's a boundary which is symmetric. Now, this last thing is a picture of calcite. And it's a three-dimensional grain structure. it happens to fracture very nicely, so you can actually see the grain structure fracturing along the grain boundaries. And the reason I'm showing you this to complement this picture is what you find out is that most grain boundaries are not flat. There's some curvature to these. And let's say this is a high symmetry plane. If this is a high symmetry plane, all the other ones are generally going to not be high symmetry. And in fact, although we like to study high symmetry interfaces are a rarity. In fact, usually they're curved, they're asymmetric. Even if the two orientations of the crystals are symmetric with respect to each other, the boundary plane may be canted or tilted relative to that boundary plane. Okay, so, and in a polycrystal, which is why we're interested in grain boundaries, polycrystals show many types of grain boundaries. And so what we want to see is what's the implications, some of the things I'm going to be telling you about, not just on boundaries, but also on how these structures evolve. Okay. So I'm not going to spend a lot of time on methods, so let me get some of this out just for completeness right from the beginning, and then I'll focus on the results. So I'll show you initially some work on molecular dynamic simulations of grain boundaries. And so what you see here is a unit cell with two grain boundaries, periodic in X, Y, and Z. Okay. Now, I can derive the grain boundary in several different ways. One, if I lower the free energy of the crystal in the middle relative to this crystal on the outside, then these two grain boundaries should move outward, such that you increase the amount of the low energy orientation. So we do this by shifting the chemical potential of one boundary, of one grain relative to the other. We call this a synthetic driving force, and that drives grain boundary migration. Now, I can also, as I mentioned a moment ago, is I can apply a shear. So if I shear the crystal like this, then it turns out that the grain boundary was here, may migrate upward at the same time as the crystal shears over. This is a general phenomenon we call shear coupled migration. It applies to almost all types of interface motion, that there's a coupling between the motion this way and the shear that way. And so if I make the boundary move like this, the crystal will spontaneously shear. And if I shear it, it'll make the grain boundary move. I can do it either way. Okay. So I will show you some results where we drive the boundary by putting on this chemical potential difference. It's the jump in chemical potential across the boundary, which we call the synthetic driving force, or by applying a shear. I'll average the data over boundary migration over distances of at least 50 nanometers. And the simulations may take anywhere from nanoseconds to many tens of nanoseconds, just depending on what I need to get good enough statistics. Okay, so that's the first part. I'll also show you some results of a simulation method called phase field crystal. Yes, no, have you guys heard of phase field crystal? No. So phase field crystal is basically as follows. Let me tell you what we're trying to do, then I'll tell you quickly how we do it. I'm not going to go through the method in detail, but the idea here is that we don't want to study the vibrations of all the atoms. I don't really care about motion on the scale of vibrations. what I care about most is motion on the time scale of, say, diffusion, so much longer time scales. And so instead of watching the atoms vibrate around, imagine what I'm doing is thinking about the probability density where an atom is. So if the atom is centered here, it's going to vibrate. And so if I ask what's the probability density where that atom is, there'll be some Gaussian that describes that probability density. And so what you should be thinking about is the evolution of the Gaussians that represent the probability density where atoms sit. Okay. And since there's no vibrations here, we can go to much longer time scales. And what we're going to do is set the overall time scale in these kind of simulations by matching those simulation results with how fast vacancies move. Okay, the point is, since you're not considering all the details of the atomic vibrations, I can't actually look at atom hopping. So it just sets a scale. Okay. And the third method we're going to use is nudged elastic band. You guys know what that is? Okay, good. So I don't spend too long on this. But the idea is what we want to do is find out the transition state, the barriers for the motion of a grain boundary. And it turns out that the way grain boundaries move is by forming a pair of what we call disconnections, which have step character. So these are steps. So if those steps, if this pair of steps migrates outward, the boundary moves up. Okay. And it turns out in bicrystals, unlike free surfaces, those steps have associated with them Berger's vectors or dislocation character. Okay. And that's, by the way, that's why you get this shear coupling, because the steps, when they move, they translate the boundary, but they also move the Berger's vectors, and that gives you the shear. And that's why the two things are coupled. Okay, so that's basically a unit cell for nucleation of a disconnection pair and propagation. This will set the barriers for the motion. Okay, so I don't want to spend too much time on the details. I want to focus on the main idea. So let me just jump to some results, and then we'll spend most of the time trying to understand what all this means. Okay, so these are data for this, again, the synthetic driving force, which is jumping chemical potential across the boundary. So this is the driving force, migration rate, so the absolute value of velocity. And for 3 different grain boundaries. And the red and blue curves there are data corresponding to what happens when I put on a positive driving force or a negative driving force. And you can see we have enough data that the error bars are much smaller than that difference. As I said before, when we did this initially, we just thought this was just insufficient statistics. So we went to great lengths to make sure that they're statistically significant. And the thing you see in all 3 of these boundaries is that the migration rates depend on whether the driving force is positive or negative. Okay. And we've repeated this for something like 25 different types of grain boundaries in 3 or 4 different materials and with 3 different kinds of driving forces. And this is the generic conclusion that the velocity in the positive direction is not equal to minus the velocity in the other direction. And I just want to point out, by the way, for those who know this notation, this is just a label for what kind of grain boundary it is. But when I write down ATGB, it stands for asymmetric tilt grain boundary, which is to say there's no mirror symmetry across the boundary plane. It's asymmetric. Okay. So those are 3 different boundaries. Now, once we start getting those results, we say, okay, let's look at the structure boundary as it moves. Okay, and so what I'll show you are some structures of the boundary when it's moving this way. And I'll show you the structure of the same boundaries when they're moving that way. Okay. So in this particular grain boundary, the sigma 27 boundary, is when it's moving this way, it splits into a twin here and another grain boundary here. So this is faceted, but it breaks into this pair. When it's going the other way, it does not break into that kind of pair. So the structure of the boundary moving that way is different than the structure moving that way. Okay, so it's not surprising that they have different mobilities because the structures are different. By the way, if I take the stationary boundary, there's only one structure, right? So moving boundaries have different structures than stationary boundaries. If I switch to this boundary, the sigma 11 boundary, it turns out that as this boundary migrates, it's broken up into micro facets or nano facets. But in one case, the motion of the boundary is controlled by the migration of one set of facets. So if you have facets here, the boundary can move down by this facet moving this way, or this facet moving that way. Either way, it'll move down. Now, whether it's moving down or up, it switches which facets control the motion. In this particular boundary, the sigma 19, it turns, well, so in this one, the sigma 11, in one case, it's only controlled by one type of facet motion, here by both. In the sigma 19, by the motion of two different facets. Now, why do I show you all that? See, my thought early on was that if I look at the structure, I should be able to see something which is the generic feature of why boundaries are different this way than that way. I always see one kind of difference. The interesting thing is every time I look at a grain boundary, especially more complicated grain boundaries, what you see is that they're different moving this way than that way, but they're different in different ways. So this boundary, what this does here is completely different than what this does. And every time I look at an asymmetric boundary, it seems to move asymmetrically in the different directions by completely different mechanisms. But it's not surprising that once the structure is different, that the mobility is different. Okay? And it turns out that as long as the boundary is asymmetric, the boundary will always find a way to move with different structures in different directions. Okay, a couple more examples, and then we'll spend most of the time today on the analysis. Okay, so these are grain boundaries driven by an applied shear stress. And you can see much different mobilities in two directions. And this boundary is kind of a weird one. I'll tell you why in just a minute. But this one, basically, the way it moves is by moving sets of disconnections, but different ones in the two directions. This is an asymmetric tilt boundary. This one's a symmetric tilt grain boundary. Now, it seems to have different mobilities in the different directions, even though it's symmetric. So why is that? Well, it turns out, by the way, if it's a symmetric boundary, it doesn't know the difference between up and down. So what's the difference? Well, it turns out that for this particular grain boundary, the boundary transforms to what we call a 99R structure. It's a long story, not really relevant for the talk. But the point is, it'll form a structure, this 99R structure, which is different up and down. But if I look over here, it'll pick at random the structure, say, pointing up. And way over here, it'll move with the structure pointing down. So if I average over a very large boundary, it's equally likely to go up and down. So overall, the mobility is the same in both directions. So this is a very special case. So even when you have a symmetric boundary, locally, it could be asymmetric, but macroscopically, it still has to be same velocities in both directions. Okay. Okay, so that was the comment I made earlier. One more set of examples, and then we'll spend the rest of the time trying to take it apart and figure out why this is happening and what its implications are. So this is typical. This is symmetric tilt grain boundary. And if I just look at the ratio, the velocity in the plus and minus directions, it's just 1. Typical for a symmetric boundary. That's a symmetric tilt grain boundary. If I pick a more complicated one, but still symmetric, again, you see the velocity is the same in the 2 directions. If I just do an asymmetric boundary, it goes like that. It's a function of driving force. And this is another asymmetric boundary, again, as a function of driving force. It looks like that. Okay, so symmetric boundaries have the same mobilities in the plus or minus direction. Asymmetric boundaries do not. And just one final case to look at is this situation. Now, normally, if you think the grain boundary is curved, the velocity goes in the direction of the curvature, minus the curvature. So if it's curved like this grain boundary should migrate this way. Okay, this is the classic experimental design by Dmitry Molodov and Laszlo Schindlerman. They looked at this for years. Now, in this case, I've just taken the 2 crystals. I put the yellow one on the outside and the blue one on the inside. So basically, I just switched the direction of the normal of the grain boundary. I've just switched the blue and the yellow crystals. And again, in this case, where the driving force is curvature, capillarity, again, you see that the migration velocities are different in the 2 directions. Okay, so conclusions from this whole part. Symmetric grain boundaries move with the same mobilities in the plus or minus direction. Asymmetric and non-symmetric grain boundaries have different mobilities in the plus or minus direction. It's not sensitive to the type of driving force, the magnitude of the driving force, which material it is. It only seems to be sensitive to the symmetry of the boundary. Okay? So let's take it apart and see if we can figure out why this is the case. So as I mentioned before, the way grain boundary migrates is you form this pair of disconnections. So these are steps here. And if I make the boundary go up, these 2 steps form like this, and they migrate outward. If it's going to migrate down, the double kink or the double pair of disconnections go the opposite direction. And then again, these things go outward. But if I look at this step here and just look at these sort of planes that I drew in, this is the same as that. And it's both moving in the same direction relative to the crystal structure. Okay, so that's moving like that, that's moving like that. They're both moving the same direction. Same thing for the red one. Okay, now I'll show this to you by looking at some of the nudged elastic band calculations. Now, this is an asymmetric boundary. So I drew the atomic planes coming up this way here, and these at an angle here. So there's no symmetry across, no mirror symmetry across that plane. If I look at the symmetry of this structure here, when it goes downward, it's like that one. Okay, just follow the lines here. You know, this is the same. And so this one, when it migrates, goes in the direction towards the slanted planes. This one, though, when it migrates, goes in the direction of the vertical planes. Okay, so it's just a schematic illustration, just to show you that when these things move, in the asymmetric case, the two directions of motion are not equivalent. They involve the same kinds of steps and Burgers vectors, but moving in opposite directions. Okay. Now, we'll do the nudged elastic band calculation to look at the barriers for motion. Okay, so this is a sigma 11110 tilt boundary in aluminum. This is symmetric boundary. There's some details about the nudged elastic band calculation. We don't focus on that. But if I look at the energy to form this double kink and propagate it out, I have a barrier that looks like this. It's symmetric, left and right are the same. On the other hand, if I take the asymmetric tilt frame boundary, same misorientation, now you can see that the activation energy profile, the energy landscape is quite different. And in fact, if I just look at part of it, you can see it's not symmetric. So if I flip this around, it's different than this one. If I flip this one around, nothing happens. Okay. So here's a simple question. What is the implication of changes of going from a symmetric energy landscape to an asymmetric energy landscape? So how are we going to look at that? Well, so those are the pictures I showed before. These are from the NEB calculations, but it's kind of complicated. I'm a theorist, so as we always do, we'll simplify it a little bit. So there's a simpler version. So I just take a symmetric curve, and this one's an asymmetric, non-symmetric curve. It actually doesn't matter what I draw, but in the calculation I'm going to show you in a minute, it's easier to assume something very simple. Okay, so now let me just assume I have these two energy landscapes, and I want to analyze how the boundary moves over long distances. So I could do kinetic Monte Carlo with these energy landscapes, but I'll do it even simpler because I don't really know what the prefactors for the prefactors of the exponentials for these cases. So what I'll do is just a Markov chain analysis. So let's walk through that. It's actually really simple, but it's turned out to be really powerful. So what we're going to do is say, well, let me define two states, A and B, the two minima. And now what I want to do is ask the question, what's the probability if I start here, at the next time step, I end up over here? Or if I start here, I end up over there. Or this just means nothing happens. Okay? So now what I'll do is I'll look at these two landscapes. And for this case, clearly, the probability of going to A to B, I'll do it from this side, A to B like that, PAB to the left, is the same as the probability of going to the right. And in this case, this one has a big barrier, and this has a small barrier. So in this case, those two probabilities are not the same. Okay, If you want to do kinetic Monte Carlo, it's fine. Just add a frequency factor to the front of it, and instead of probabilities, you have rates. Okay, so what I'm going to do is start the boundary at one position and just keep evaluating its transition rates based on these probabilities. Okay, so for this case, so we're going to say right here at the site 250 at time equals 0 at the first step. The boundary is definitely there, so the probability is just a delta function. And then as time goes on, I get these other black curves. So basically, in the case of a symmetric situation, the boundary is just doing random walk, left, right, takes steps at random. Well, this we know this from diffusion. The solution of that is just a Gaussian. And as time goes on, the Gaussian spreads and the peak goes down. And so the probability of the boundaries at any position at any time, you just calculate according to those probability distributions in black. Now what I'm going to do is go back and take this energy landscape here, and I'm going to tilt it to the right, which is the same thing as putting on a force in this direction. So now what's going to happen is I start at time equals 0 where that black curve, where the delta function is here. And then the next time, the probability distribution is this one, this one, this one, this one, this one. And so it's migrating to the left. Okay. It still gets wider and wider, but it migrates always in that direction. On the other hand, if I take this and tilt it like that, the probability distribution spreads, like you see in blue here, and it's moving to the left. And so the boundary is moving towards, your left, moving towards your left, moving that way, because the peak position is shifting towards the left. Okay, so in that case, the mobility, that is the position of the boundary at the same amount of time later, if I tilt it, if I put on a driving force, positive driving force, or a negative driving force, will get just as far, but in opposite directions. Now, if I go to the asymmetric case, when the driving force is 0, it spreads in exactly the same way. It's just a spreading out of a Gaussian. It's the boundary's position is diffusing, spreading out like a Gaussian in black. On the other hand, when I tilt it this way, you can see it moves to the right. And if I tilt it that way, tilt it like this, it moves to the left. But you can also see this getting a lot farther this way than that way. So you have the probability density is evolving faster in one direction than the other. Okay. So what I'm trying to show you here is just by making the energy landscape asymmetric is enough to show that the boundary migration rates in the two directions are different. Okay. Now, the other thing that's kind of interesting is if the force is 0, I don't tilt it, it's exactly the same. So this is only something for a moving boundary. Let's see. So again, the point is asymmetric energy landscapes give you asymmetric boundary mobilities. And by the way, I hope I emphasize it enough, but it doesn't matter why the energy landscape is different, whether it's symmetric or asymmetric. It doesn't matter why it's asymmetric. It's just enough that it is asymmetric. Okay. Let's make it a little bit more interesting. So if I put on a driving force to the left and say it moves faster to the left, and when I switch the driving force, make it move to the right, if I oscillate the driving force, like put on a stress that's oscillatory, the boundary will have net motion in one direction if it's non-symmetric. So this is the distribution. You can see it's spreading in that direction when you put on an oscillatory driving force. And if it's symmetric and you put on an oscillatory driving force, it doesn't move on average. Okay? So that's kind of interesting because it suggests ways we can move boundaries. Let's make it a little bit more interesting. Let's just say I do cyclic annealing. Heat, cool, heat, cool, heat, cool, heat, cool. If it's symmetric, it just spreads out uniformly. However, if you use cyclic annealing, when the energy landscape is not symmetric, you get net motion in one direction. Okay, this case I think is pretty clear because when you put on a plus driving force, it moves farther than when you put on a minus driving force. It doesn't go back as far. This one's a little bit less clear, so let's spend a minute talking about that. By the way, this whole kind of motion are known as Brownian ratchets. Biologists know all about it. If you look in Feynman's book from the 60s, it's in Feynman. I mean, it goes way back. So again, let's imagine you have a particle sitting in an asymmetric energy landscape, sitting right there. Now, heat it up, and the particle wants to diffuse. Just it gets a Gaussian distribution, just spreads out. Now, if I cool it, then any time that it's from here over, it's going to fall down into that side. On the other hand, this part here, if I cool it from here, it's going to fall back down to here. So if I keep doing this, the net probability, the net rate of motion will be to the right. Okay, so that's what heating and cooling does. This is just spreading it out like the Gaussian we saw before. This is what happens when you let it spread and then quench. Let it spread and quench. Okay. Now, if I just change the temperature a little bit, you know, these are all very small, just the probabilities are not quite as extreme as I drew it there, but the same idea works. Okay. So just to recap, what I tried to show you is for a given grain boundary, if I put on a certain driving force in one direction, it's an asymmetric boundary, it'll migrate faster in one direction than the opposite. I try to give you an explanation of why that is. Now and I try to show you that if I put on an oscillatory force, it'll move net in one direction, or an oscillatory temperature, cyclic annealing. So let's do that in a simulation. So if I take a symmetric boundary and I put on an oscillatory driving force, it goes left, right, left, right, left, right, left, right. Okay. If I do this for a case where the boundary is not symmetric, you still get left, right, but there's a net drift in one particular direction. So that's from a molecular dynamics calculation. If I put on, that's with an oscillatory, say, chemical potential difference between the two grains. If I put on an oscillatory stress, you know, push, pull, push, pull, push, push, pull, push, pull, like that, fluctuates up, down, or left, right, Same thing if it's a asymmetric boundary, but there's a net drift this way. Now, that's all done molecular dynamics. I could go to long time scales by doing this phase field at the phase field crystal method. And notice the difference in time. This is nanoseconds. These are tens of milliseconds. Okay, a little bit more realistic. And so we do it for the oscillatory, in this case, oscillatory temperature. And not much happens. This one, clear migration. You can measure the slope, and that's the velocity in that direction. Okay, so I've showed you stress-driven, chemical potential-driven, oscillatory fields both ways, oscillatory temperatures, thermal cycling. Does it really happen experimentally? So my collaborators did a study here. What they do is they take a textured thin film of nickel. They do EBSD and measure the orientation of all the crystals. They find a grain boundary they like. They use a fib to cut out a sample. So now they have a bicrystal. And they put a heater on, and they heat and cool it. So they did it heating and cooling. The temperature was 400 plus or minus 50 degrees. They did it at 0.33 hertz, and they did it for 20 minutes. And so you can see the difference in orientation of the two crystals. It's electron diffraction pattern. And so you can see it's not symmetric. And here's the position as a function of time. So after 20 minutes, it's there, and there, then there. So the total distance it's migrated, I didn't write it down here, but let's see. So this is half a micron right here. So this is the grain boundary displacement as a function of time. And first what they do is they hold it at 400 degrees C for a while, and the boundary doesn't move. It's a flat boundary, the temperature is relatively low. I put on the oscillatory driving force, plus or minus 50 at this frequency. And the data is not perfect. This was the first experiment on the thermal cycling. You get a migration rate of 0.34 microns per hour. Not a lot, but it's, I don't know where the maximum rate is. And interestingly, if you go and hold at the higher temperature, you still get some small amount of growth. But that's just because these two crystals have different normals. And the surface energy of this is different than the surface energy of that. So the difference in surface energy will still give you some migration, some driving force in one direction. Okay. So I think it's very nice experimental confirmation of the migration. I won't show you the following, but let me mention it. Colleagues also just took their bicrystal and put an electron beam right at the grain boundary and moved it back and forth, passing over the boundary many times. So it's not really thermal cycling because the thermal conductivity is quite high, so it's pretty much isothermal. But even so, and I don't know why this works, but when they go back and forth over many times, you still get some net migration in one direction. And if they increase the frequency, the migration rate goes up. I don't have much to say about that one, simply because I don't really know what the driving force is in that case. And it could be defect fluxes or something like that. I don't know. I don't want to speculate too much. Okay, one last thing to show you. And that is what happens in a polycrystal. By the way, as I showed you at the beginning, grain boundaries themselves, I think, are very interesting. However, usually we care about it, what's going on in the microstructure. Okay, so we made a polycrystalline microstructure. And as we anneal it, we put on an oscillatory uniaxial stress below the yield strength of the material, just like that. With no oscillatory stress, there's the mean grain size versus time. And when you put on that oscillatory stress during that annealing, you get roughly a factor 2 increase in the rate. Oops. Now, we've also gone through and done the same thing, but putting on an oscillatory temperature that is thermal cycling. And this is the PFC, the face-field crystal. Again, notice the difference in time scale, 8 orders of magnitude. And again, when you do the thermal cycling, you get this curve. And when you do the cycling and do without the thermal cycling, you do that curve. Now, there's a little question about, did I cheat? And let me tell you how you can cheat, and then I'll tell you how to do it. Actually, this is a good quiz question for students. How would you cheat? Well, the way you cheat is very simple. When you hold it at the temperature, say 400, and I go plus or minus 450 and do plus or minus 50 degrees, since at 500 it goes much, much faster than at 450. If you do it at 400, it goes slower. But the net effect is you're going fast. You have the same amount of time where you're going fast. And then the same amount of time you're going slow, but it doesn't average the same thing. So I can actually take those two curves and do this correctly. And I don't have it here, but you can show that this curve is way above what you would expect from just the average of the hot and cold. So if I held it at say 500 for 10 minutes, and then I held it at 400 for 10 minutes, you get a curve like that. But when you oscillate it, it's like that. Now, a couple questions. What frequency do I have to oscillate temperature to the stress? Well, if I do at 0 frequency, there's no effect. If I do it at infinite frequency, there's also no effect. So there's a maximum somewhere in between. And unfortunately, as of right now, I don't know where that maximum is. So it depends if I do these calculations different ways. If I do it at a high temperature, say, and it could slow down as I go to higher frequency. But if the peak is here and on this side, if I change the frequency, it can slow down this way or slow down that way, just depending on which side of the maximum of the rate versus frequency. So I just don't know where that maximum is. So I think you can get much higher rates than I'm showing, but this just happens to be one observation. Okay, let me wrap it up. So the point is, Brownian ratchets are something we've known about for a long time. As I mentioned, Feynman in his lectures on physics talked about this in the 1960s. The 2016 Nobel Prize in Chemistry was for molecular motors, which are basically Brownian ratchets. So if I just shine light on it, or I put on an oscillating field and get it to walk. This is Feynman's thought experiment. So what he did is he put in an axle here, put a ratchet on this side, and on this side the atoms are hitting it at random on this side of the paddle or that side of the paddle. So it's just vibrating. The net result, though, is that that mass goes up. So something's doing work. So where does the work come from? This is a perpetual motion machine. Teaches thermodynamics. Right? It looks like a perpetual motion machine, but in fact, it's not. And basically, what you're doing is you can go through an entropy argument and show that basically what's making the mass go up is is decreasing the entropy in on one side, one part. So the system's entropy would be going down. So just an interesting thing. Okay, but the point is Brownian ratchets are a generic feature of transport under a fluctuating field in asymmetric systems. Now, if I have a grain boundary, I can show you lots of examples of grain boundaries. If I take an interface between two phases, those are almost always asymmetric. If I take a dislocation in a non-centrosymmetric crystal, look at the core structure, its motion this way and that way will be different. Classic examples is screw dislocation motion by cubic materials. So by putting on a stress, I should be able to do this experiment. Imagine you look at the stress strain curve in a material, single crystal, and I repeat it where when I superimpose on top of the stress, this little oscillation, it should be different. It's a macroscopic experiment. If you're looking in a TEM, you should be able to see it as well. So I think it's actually quite generic, and it really only has to do with the symmetry or asymmetry in the structure, the consequential symmetry or asymmetry in the migration barrier profile. And once you have that, all this other stuff just follows. So thank you for your attention, and a pleasure to be back here at EPFL. Thank you.
Thanks for the wonderful talk. I think we have a few minutes for a couple of quick questions. So maybe we'll start with people in the audience here first, and then we'll move on after. Yeah, the back.
Thank you for the nice talk. I have a question more related to the molecular side or atomistic side. How do you define the position of the grain boundary, and do you see when it moves, changes with the oscillation? Probably it also changes its thickness, right? That it has some mechanism how it's migrating related to that.
Okay, so first, how do you see it? Well, in atomistic simulations, since atoms are distinguishable, I can just count how, I take a bicrystal here and, make it periodic. So I've got two boundaries. I can just see how big the crystal is in between the boundaries. Is it getting smaller or bigger? So that's really easy to see. In terms of the crystal, right? So that tells me whether I get net migration in one direction or the other.
So it's basically just the structural parameter, how ordered your crystal or atoms are.
Yeah, there's many ways of measuring it. I can also measure the boundary position relative to, a fixed atom down here and watch how fast it moves. Or like I said, it's easy to measure the relative size of the two crystals in the bicrystal. You also asked about the thickness of the boundary. Thickness is a very hard thing to define. because this is a discrete, this is discrete. And so does it get thicker or thinner? I don't really know the answer to that, but I know if I keep doing it, putting it, say, an oscillatory stress or a fixed driving force, I can see if I stand far enough back and look at it, I really can't see that thickness anyway, and it's not getting thicker and thicker and thicker. So it may be doing this as it migrates. I don't know. And I would add that I'm not sure it's terribly relevant because we're talking about long distance motion. So any fluctuation you may have, over time would all average out. Yeah, not a great answer, but.
Yeah, thank you.
Okay, maybe one final quick question and we'll kind of
Thank you. So in your analysis, you were switching a bit between the concept of motion on an energy profile or on a free energy profile. And I was wondering if that is a delicate switch or not, in particular for the temperature-driven migrations.
Yeah, right. It's a good step back question. So I could write it down either way. It's usually easier to write it down in terms of an energy profile instead of a free energy profile. And when I was drawing those pictures, and it's just a schematic, that was based on an energy profile. Free energy is in a dynamic case, a little bit harder to think through. There may be a good way to do it. I haven't thought it through.
No, I think that there are, and it would be fun to try it, I was thinking. But in particular, what I was thinking about is the fact that, of course, the free energy depends on temperature in itself, right? And so when you try to write this combination of things, you may have different types of effects that kick in, possibly at higher order in temperature, but
yeah, I agree. And I think, as you mentioned, I think it should be of higher order. But yeah, there's a lot of room to do this, but the good thing is the biologists have been thinking about this for a long time. And, by the way, I told you Feynman sort of gave a nice simple model of this, but it actually goes back before Feynman. So it probably goes back to the 1950s or something. So there's been a lot of thought about it. I think I need to learn more about what the biologists have done. And by the way, I'm not claiming to have discovered this Brownian ratchet idea. In fact, it's quite old. I mean, the fact that we can see it in defects in crystals just based on these symmetry arguments, I think is the new part.
Thanks, Anirudh. But I think if you go back to the Tokmakov-Dill picture, some way the key statement is equilibrium versus non-equilibrium, because if you have equilibrium thermodynamics, you have the same probability to go on the left and on the right, because it's all based on the energy. Absolutely. And if you have non-equilibrium, instead the overcoming the peak on the right is easier than overcoming the peak on the left.
Yeah, absolutely. Yeah. I mean, that's exactly what the issue is. Yeah. And in fact, when I showed you the case for the symmetric and the asymmetric boundary, when there's no net driving force, the probability distributions were exactly the same.
Yeah.
That's good. If it wasn't, I'd be worried.
We wouldn't be alive, probably.
Well, that's another question, but yeah.
Great. So what we'll do in the interest of time is, if you have more questions, maybe you can come speak to Dave after. But for now, we'll thank you and.